everyone, my name is K. Srinitya, bearing roll number 458. Now I am going to discuss about vector random variables and joint distributions. What is a vector random variable? A vector random variable is a collection of multiple random variables considered together as a single entity. Rather than analyzing outcomes one at a time, we capture the complete multidimensional picture simultaneously. Mathematical notation. Here random variable is represented as capital X is equal to here multiple random variable is present. They represented as x1 comma x2 comma and so on xn. Each xi is a random variable where n number of random variable is present. In real world example, height and weight measured jointly on a single person. Multidimensional outcomes. Model complex phenomena with multiple dimensions. Joint distribution function. The definition and meaning of joint distribution function. Here, joint distribution function can be represented in capital letters. Joint PDF. The joint cumulative distribution function. Here, joint distribution function can also called as cumulative distribution function. Represented in capital letters. CDF quantifies the probability that all random variables simultaneously fall below specified their holes. It represents the complete probabilistic behavior of the entire system. In two variable case, the joint distribution function is represented as f of x comma y of x comma y is equal to p of capital X less than or equal to small x comma capital Y less than or equal to small y. The probability that x does not exceed small x and y does not exceed small y simultaneously. In general form, if n number of random variables are present or n number of events are present, it is represented as fx of x1 comma x2 comma and so on xn is equal to p of capital 1 less than or equal to capital X1 less than or equal to small x1 comma and so on capital Xn less than or equal to small xn extends to any number of random variables. Here joint probability mass and density functions. In discrete case, joint probability mass function can be represented as small p of x comma y is equal to capital P of x is equal to x comma y is equal to y. Here sum of all probabilities is equal to 1. For example, if two dice rolls, each outcome pair has probability 1 by 36. In continuous case, joint probability density function is represented f of x comma y and their integrals the area under integration is equal to 1. Here integral of integral f of x comma y dx dy is equal to 1 describes probability density over a continuous region is equal to 1. Properties of joint distribution functions. Understanding these fundamental properties is crucial for working with multivariate distributions and ensuring mathematical consistency. Here, non-decreasing property. The property reveals if f increases or stays constant as each argument increases. If each argument is increases, the f also increases or stays constant. Boundary conditions of distribution functions. If f is integrate with respect to both x comma y tends to infinity, their value is equal to 1. If either x or y tends to minus infinity, their value is equal to 0. Here probability extraction can recover marginal distributions by taking limits. Marginal distribution functions extracting individual behavior in simple words. Marginal distribution functions can be obtained from the joint distribution functions. Here the complete explanation. Marginal distributions allows us to understand the behavior of individual random variables by removing the influence of others. If we want x, we remove the influence of y. If we want y, we remove the influence of x. They represent the signature of a single variable within the larger multivariate system. In discrete variables, marginal probability marginal function of x is represented as px of x is equal to summation y into p of x comma y. Sum of joint probabilities are all y values. In continuous variables form, marginal probability density function of x is represented as small f of x of x is equal to integral f of x comma y with respect to dy. Here, integrate joint density or on y values. If you want x in terms of density or distribution functions, here the marginal distribution function can be obtained. If you want x or y values, we integrate with respect to other value, we obtain the fx of x or fy of x. Conditional distribution and density function. In simple word, conditional distribution function is obtained as if already one is happened. Based on that happened event, we follow the other event. We made the other event. Here, conditional distributions reveal how one variable behaves when another is fixed to a specific value. They are essential for understanding dependence relationships and updating beliefs based on new information. In discrete case, it is represented as p of x by y. Here, y is a fixed random variable when x is happened. Here, it is represented as p of x by y is equal to p of x comma y by p of y. Probability of x given y is equal to small y. Conditional on y being observed. In continuous case, f of x by y is equal to f of x comma y by f of y. Conditional density updated by the observed value. Key insight. It reveals dependence. Independent variables have p of x by y is equal to px of x. For example, in campus job selection, there are 2 juniors and 3 seniors apply for a 2 position selected randomly. This example illustrates joint, marginal, and conditional distributions in a campus in a concrete setting. Here, possible outcomes if there are 0 seniors, 0 juniors, or 2 seniors. Joint probability represented as P of 0, comma 2 is equal to 3 by 10. Here marginal if juniors are 0 అయితే P of x is equal to 0 is equal to 3 by 10 comma P of x is equal to 1 is equal to 6 by 10 P of x is equal to 2 is equal to 1 by 10. Here other possible outcome if 1 junior 1 senior. Joint probabilities as represented as P of 1 comma 1 is equal to 6 by 10. Here other possible outcome if 2 juniors 0 seniors are there P of 2 comma 0 is equal to 1 by 2. We use only 2 position because there are 2 positions are remaining in the campus job selections. Here the real example in campus job selection. Visualizing joint and marginal distributions. Joint and marginal distributions gives us insights of height, shape, relationship between one random variable to another random variable, and their behavior and their randomness. It gives the information about that random variable. Here, visual representation transform abstract probability concepts into intuitive insights. These displays reveal relationships, dependencies, and distributional shapes that guide statistical inferences. Here, below pictures represents the shape, height, and the dependence relationship between one to other, and distributional shapes and guide statistical interference. Here the summary. These concepts matter. Here, mastery of vector random variables, joint distributions, and their properties forms the mathematical foundation for modern statistics and data science applications. In model complexity, vector random variables capture multidimensional phenomena accurately. Here, probabilistic relationships. Joint distributions reveal complete interdependencies among variables. Focused analysis, marginal and conditional distributions enable investigation of specific aspects. Real world applications essential for multivariate statistics, machine learning, and data science. Now we are discuss about the topics one by one. First, vector random variable. What is a random variable? How many random variables are there and how it was represented? And another one, joint distribution. Joint distribution is represented in capital letters. Joint distribution functions are represented in capital letters, and we obtain marginal distribution functions from the joint distribution functions and their properties. And joint density functions are also discussed. From joint density functions, we obtain the marginal density functions, and joint distribution functions are also called as cumulative distribution functions. And we discuss so many properties of the and real world examples.